In this video, we're going to consider the geometry of pi bonds and how they influence the overall shape of a molecule. Our learning goal will include the orientation of those pi bonds relative to a trigonal plane. Our assumption here is that the pi bond is, generally speaking, going to involve a carbon atom, which forms normally 4 bonds. With the pi bond, that means it's got a double bond, so it forms a total of 3 bonds, so its geometry should register as trigonal planar. So we're interested in how the pi bonds relate to that trigonal plane. Recall that pi bonds arise from the overlap of two p orbitals. So it looks something like this. We have two p orbitals that approach one another. They are vertically aligned in the case of this picture, and they are parallel to one another. They have to be in order to make the pi bond. If they're not arranged in parallel tandem with one another, they can't make the pi bond. So if we look down the axis of this bond from the side, we see the sigma bond in the middle. That is the region that's connecting the two atoms, and the pi bond lies above and below that sigma bond. So we can think of that pi bond as having a vertical orientation, at least as it's drawn here. It's an orientation that's up and down relative to the axis that connects the two atoms. The picture actually looks a little bit like a hot dog, where you can think of the sigma bond as being in the middle and the pi bond being the buns that layer it on either side. Now, how does this influence the trigonal planar structure within a molecule? All right, so let's, for example, consider the beginning of a pi bond in a molecule, and it is formed, for example, by a carbon atom that is in a trigonal planar structure. It's got 3 other bonds. That's what forms the trigonal plane, and the 4th bond is the pi bond. All right, that molecular plane is defined by the trigonal plane. All right, so that's where all of the atoms are lying in this case. The pi bond itself is oriented perpendicular to that plane. So if we look down the end, we can see that even more clearly. The sigma bond there is in the middle, sandwiched by the 2 halves of the pi bond. That's the sigma bond that is part of that double bond structure in the middle. And the molecular plane there is oriented, and it splits between the 2 halves of the pi bond. The pi bond electron density is going to lie above and below that plane, okay, and that's always going to be the case. But now we can use this arrangement to anticipate something else about the relative orientations of pi bonds and the atoms in those pi bonds. If we have 2 carbon atoms forming that pi bond, they must both be trigonal planar centers. So I've drawn them like this. Okay, in both cases, the p orbital has to be perpendicular to the plane of that trigonal planar arrangement. So when they come together to form a sigma bond first and then a pi bond, they're going to form 2 trigonal planar centers that are attached to one another. And the pi bond that they form is now going to sandwich each of the trigonal planes. Okay, so what does that imply? Well, that pi bond has to be perpendicular to both planes, and this is what forms overall a molecular plane that contains not only the 3 atoms attached to one carbon, but all 3 atoms that are attached to the other. So in other words, all 6 of these atoms are going to be in the same plane surrounding that pi bond. So whenever we have a pi bond between 2 carbon atoms in an extended structure, it's actually going to really imply that we have a planar structure in the middle of that molecule that contains 6 atoms, the 2 that are bonded to one another and the 2 atoms that are bonded to each of those 2. So this is something that's going to be very important when we consider, in Module 5, we consider extended pi systems that are conjugated.